There we go. Now we are recording. So, no questions about building sums? Okay, in that case, I'm going to give you a very nice one that you are going to be using constantly for most part of the following 10 years, and that's number 11. So we have this sum here, 1 plus x squared plus all powers of x all the way till n. Now I'm going to do a small parenthesis here and say that 1 is x in power 0. Why, you may be wondering. The reason why is when we give values to I here, we can say that our sum starts in 0. Then we have 1, then we have 2, then we have n minus 1, then we have n. In total, we have n plus 1 terms. And here it's term that we are going to call a sub a. I'm just hoping this is seeable in the whiteboard. Yes. Here it's term of this succession, which we will call a sub I, is x in power I. The term 0 is x in power 0, the term 1 is x in power 1, term 2 is x in power 2, etc. So our sum is the sum from I equals 0 to n of x in power I. And now comes the interesting part. And is that if the absolute value of x is smaller than 1, this is no other than 1 over x minus 1. If you want to prove this, you do your typical polynomial division in this way, and you will see. Actually, you only need the absolute value thing in the infinite case. What a nice result indeed. However, when you're going to use it, remember that if you're working with something in such a way that x equal 1, you won't be able to, but still, this works pretty well. The reason why is this is a geometric function, this is a geometric succession in which the reason is no other than x. And so by using the formula for geometric progressions, you have that this finite sum is the first term over the thing you multiply by minus 1. Now, questions. This is a very beautiful one, so please don't ever forget this. 1 over x minus 1 is the sum from 0 to n. This is called a cyclotomical polynomial, actually. Of degree n. Now, questions about the cyclotomical polynomial? Does it work for all x? No, it doesn't. And this works if x is different than 1. Now, for Thursday, I want you to check whether or not this is true, and if and where I'm doing the mistake. If you want to see it clearly, you can see, for example, x equals 666. Replace it here and see that it doesn't work. Now, moving on, we have number 17. And it says, we have to find a closed form for this thing here. Now, we have said that sigma is a sum. So the first thing we can do is split this as the sum of two sums. Why? You may be wondering, because this one is very simple. This thing right here this is twice the sum of all natural numbers up to n. So it's something like that. And now what do we do with the other one? Ideas. Give me ideas. Didn't we get a formula on the lecture for exactly that? Oh, you absolutely did. So the answer to this thing is yes. This sum here is n plus 1, 2n plus 1 over 6. And there we go. Now, if you want to see why this and these are the same, you actually don't have to believe me. You have already learned a beautiful and very powerful mathematical tool known as induction. And one of the main applications, actually the first application I saw of induction, is that formula over there. Obviously, this is probably not even worth mentioning, but this goes to infinity very fast. This approximately 2n cubed. So if you find this sum, but instead of having a finite ending here, you have an infinite ending, you have what is called divergence, which is a sum that becomes very strong. Okay. Now, next thing, number 21. You may be wondering, how in the world are we going to sum all the logarithms? Well, I'm going to find this sum. In this way. And please stop me if you don't believe this. Now, what did I do there? You took out the logarithm and then took e on both sides. Pretty good. So actually there is an intermediate step. And this is by using log properties. Equal to this thing over here. So yeah. So, however, we have a mathematical symbol to express this product. Since m is greater than 0, which is implicit in this sum, what we are going to do is I'm going to define you the factorial of m as 1 times 2 times 3 times the product of all smaller numbers than m up to m. So by considering this, we have in power s is the logarithm of m factorial and there we go. So yeah, you may be thinking, if we knew about the factorial already, we could have skipped a lot of steps because here we are finished. And you are right. Here the problem is solved. Now, what I want you to notice here is that sigma notation is scary. It can be pretty scary sometimes. But in the end, I want you to remember that this is a sum of a lot of things. And so the way you operate with sigma notation is the exact same way you operate with sums. You have a sum of a finite number of logarithms, which is what I want you to acknowledge. Now, moving on, we have a telescopic sum. In J. Okay, I'm going to give you the solution and you're going to tell me why. I did my part. Now it's your turn. No one? Okay. Then let's do it. First term is 2 in power m minus 2 in power m minus 1. Second term, 2 in power n minus 1 minus 2 in power n minus 2. Third term, 2 in power n minus 2 minus 2 in power n minus 3. Now we're going for the second term, 2 cubed minus 2 squared. Second term, 2 squared minus 2 in power 1. And finally, for the last term, we have 2 in power 1 minus 1. So how does this work? This works like this. You pick up your erasing tool and you notice this thing. This cancels down. This cancels out. This cancels with something that is here and I'm not going to write. This cancels in the same way. This cancels in the same way. This cancels in the same way. And what we have left is 2 in power m minus 1. If you're working with a sum, one of the easiest thing to check is if it's telescopic, because you write 3 or 4 terms and immediately, bam, 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 they start canceling out, and that makes them for some really easy calculations. Now, questions about telescopic sums? What did it mean to be telescopic? Telescopes fold. and this sum falls in the same way. You have it completely expanded, but then you start looking at it, and it shrinks down to a very portable size. We went from 2n terms to 2 by just folding it. So the idea of telescopic is that they fold. All right. Then, since it's already 11 a.m., let's flex a little bit our mathematical muscles and do something interesting. So number 40. Number 40, we have this identity. Which is absolutely nothing from the other world, nothing strange. K plus 1 in power 4 is K4 plus 4K3 plus 6K squared plus 4K plus 1. Nothing new under the sun. So we want to write n copies of that identity. I'm going to spoil you something. I'm not going to write as that many copies of that identity, but I'm going to write a couple of them. If k is equal to 1, this is 4 plus 6 plus 1 plus 4. And if it's equal to n, this thing right here. So what we want to isolate here is the sum of the cubes. In order to do that, I'm going to write this down as a sum using sigma notation. Starts in 1 or it starts in 0 in 1. This thing right here. So what I want is to isolate that part. So we're going to take all this part of the sum and move it to the other side and see what happens. But first, I'm going to do some magic. This, let's see if this works. it kind of works. This is a difference of two squares. So look at this. Is okay. So I'm going to try and separate this. Here we have 2i plus 1. And here we have 2i squared plus 2i plus 1 equal to that thing over there. That was a mistake. I actually cornered myself. Okay. Now, other thing we can do is try and solve this. We're going to start here. Now, this sum is 6 times the sum of the n first squares. So this is n plus 1, 2n plus 1, plus 4 times the sum of the first n natural integers. That's 2n plus 1 plus n. And so we leave this be. This is a minus, this is a minus, and this is a minus. And the reason why I was doing a mistake with this difference of fourth powers is that it's telescopic. So let's see what we have here. Sorry. So this is first part of the first term minus last part of the last. So this is n plus 1 in power fourth minus 1. Minus, I'm going to start unraveling this, 2n cubed minus n squared minus 2n squared minus n minus 2n squared minus 2n and minus n. So does any of this cancel? No, it doesn't. Okay. So we start moving the terms here, 2n cubed. I don't like this 5 for some reason. For the 2. Minus 5. Now we put the n's together. And those are 4. Boom, boom, boom. And minus 1. Okay. We're almost there. Now I need space. We move to the other side of the whiteboard. And we have, I'm going to expand this. Sorry. This is equal to n fourth plus 4n cubed plus 6n squared plus 4n plus 1. And now minus 2n cubed minus 5n squared minus 4n minus 1. So we can start canceling things here. This cancels here, this cancels here, this cancels with this, it becomes a 1. So this is n fourth plus 2n cubed plus n squared. And now is when the magic begins. A perfect square, ladies and gentlemen. So finally, this 4 comes out, and we have boom, we got it. Now, this was absolute magic. I love it. So the idea here is that we have expanded I plus 1 in power 4 in all of its powers, and then we have built a telescopic sum with it, which actually cancels out in a very nice fashion. And in the end, all we have to do is some fiddling and some meddling with the ends. So the coefficients actually cancel in a very nice fashion. And the last step of the exercise, we just realize here is n squared common factor of a perfect square. Beautiful, huh? Now you may be thinking, why would one use this kind of approach to find out what the sum of a certain number of cubes is? We know the sum of the first power, we know the sum of the squares. The cubes always give us a little bit more struggle. So this is most likely the approach someone else used many years ago to figure out what this was. One common way to figure out about the value of certain things is to put them into context. To be concrete, a very important part of the work in mathematics is to find the proper context in which things have nicer forms, and that's how you solve complicated equations. Sometimes the sum of the cubes comes from the expansion of the fourth degree equation. Other times, even funnier things happen, but we will see some of those after the break. 10 minutes. We'll be back at 19 past. Okay, so let's do Riemann partitions, I guess. So the idea of the integral is that it's the limit of a sum of rectangles. So let's do a sum of rectangles and see what is happening. We have x cubed in the interval 0, 1. And we want to find this integral as the limit of a sum of rectangles. So first of all, we're going to calculate the lower sum of rectangles, and then we're going to calculate the upper sum of rectangles. Now let's draw our coordinate system. We're working in 0, 1, so this the graph of x cubed looks something like that. And our partition is 0, 1 over n minus 1 over n, and 1. So we split this thing into n equal parts. So which one do you want me to begin with, lower or upper? I don't have a red pen. Anyway, let's see one of these values work. Now, in blue, I hope you can see it. We have the upper sum, the upper rectangles, and in green we have the lower Riemann sum, the lower rectangles, right here. So we're going to be working with the upper sum first. And we notice that in each rectangle, the area of each rectangle is 1 over n, which is the base, times the height. And the height of the ith rectangle, which goes from I over n, from I minus 1 over n to I over n, is none other than this thing right here, which is the value of the function in the extreme where it's largest. And of course, we are summing here, so it's important to notice. From 1 to n, because we have n partitions, n rectangles. That thing right there. And now for the lower sum. This is the base of the rectangle as well. And here, instead of having the point with that is tallest, we have to take the one that is shortest. since this is uniform increasing, we have to take the other extreme of the interval. In our case, I minus 1 over n in power 3. Now, we have our two Riemann sums, upper Riemann sum, lower Riemann sum. Now we have to calculate the limit when n tends to infinity of the upper sum. That's the limit when n tends to infinity of the sum here. And if we remember correctly from the last exercise, this is n squared, n plus 1 squared, divided by 4n 4. This 4 looks good, doesn't it? Of course it does. There's a limit of two polynomials in the infinite. Both have degree 4. So this limit is no other than 1/4. Now, in order to solve the other one, we may have to do some magic. So let's see what happens here. We have limit when n tends to infinity of the lower Riemann sum. Now this doesn't look as good anymore, but this is one thing we can do. And now, here, in order to convert this into this, I need to add and subtract something. So what do I have to add and subtract? First of all, the term 0. I have to subtract that, but it's not going to be a problem because it's 0. And now I have to add and subtract the term n. The term n is this thing right here. And since I have added it, I have to subtract it as well. Is this correct? Term 0, this is 0 here. Add determine n, subtract determine n. So we should be good to go. Now this is the limit when n tends to infinity of the sum. Do you see this? Okay, you're done. Let's move this a little bit. And let's do it in a different way, actually. Yep. You may be already noticing that calculating Riemann sums is sometimes more difficult than integrating, but it happens. One, two, three, and four sums. Let's see what happens there. This is not a 2, this is a 3. So this sum minus 3 n plus 1 to n plus 1 over 6 and 4 plus 3 n plus 1 over 2 n fourth and minus n over n fourth. I'm losing the last term. And all this is within the limit. Now, if we evaluate this thing in the infinity, what happens? Polynomial of degree 4, polynomial of degree 4, the limit of this is 1/4, minus 3, polynomial of degree 3 over polynomial of degree 4, this is 0, plus 3, polynomial of degree 2 over polynomial of degree 4, this is 0, minus polynomial of degree 1, polynomial of degree 4, this is 0. One-fourth. What's interesting here is that both limits coincide. And if the limit of both Riemann sum coincides, then that's the value of the Riemann integral. Now, questions about Riemann sums.
Is there any difference between the upper or lower when it comes to like accuracy?
Yes, there is. The two Riemann sums are almost always different. Actually, the only case in which both Riemann sums are the same is when the curve is a straight flat line. In that case, the rectangles that go below are exactly the same as the rectangles that go above. Otherwise, this is a very nice integrability test, because there are some functions that are especially non-elementary functions that it's hard for you to calculate continuity, but there is actually something you can do here with the Riemann sums. And then you can talk about whether or not the function is integrable. And from then you may learn something about continuity. And with this being said, let's never do a Riemann sum again. except for the next exercise that I'm going to do. Yeah. Pen. No. So we have number 11. We want to express this as a Riemann sum. Or more concretely, as a definite integral. In order to do that, I'm going to try and figure out which function it belongs to. This is x, this is y. If we do a partition, I don't know, from 0, 1, then all we have is we have rectangles with area 1 over n. So our interval goes from maybe 0 to 1. And here, if we see this as rectangles, that's the image of the point I. So in the ith part of the partition, we are taking the image at I over n. So we are dealing with something like that. So if we want to express this as an integral, this is obviously the upper Riemann sum of this function, and so our integral goes we move in the interval 0 to 1. For example, yeah, we are definitely in 0 to 1. And our function here is square root of x, because it's the one that defines the height. The base is fixed, the height is determined by the function, and since this is an integral, we add the x at the end, which means with respect to x. Funny enough, if we do number 12, number 12 is actually the same. But instead of consider the upper Riemann sums, it's considering the lower Riemann sums, this thing over here. I mean, you may see two exercises in a row that may or may not have the same solution. You arrive to the same solution, and then you spend maybe more time than you should wondering why two exercises have the same solution. Well, they could be literally the same. In this case, the square root of x in 0, 1 is perfectly well defined. So this works. And now, actually, this is the first time it happens during this course, but I ran out of recommended exercises. And I really, really, really don't want you to spend too much time doing Riemann sums. So maybe now is the time for more and more general questions. Will we ever actually use Riemann sums? Yes, you probably would. Yes, you probably will. Sorry. What I want you here to acknowledge more than Riemann sums themselves is the concept of partition, which is by far more important. Also, when working with elementary functions, you most of the time will stick to Riemann integrals, but then we will see. I don't know if that's within the scope of this course, but there is another way of integrating that is called the Levesque integral, which is much more powerful than the Riemann integral, but you have to understand very well the concept of partition to see how it works. And that's how you go into several dimensions and integrate complicated stuff. For now, let's stick to this limit of rectangles. It also grinds to the notion of the integral as area. And don't get this wrong, the integral is not an area. One of the uses of the integral is to calculate the area below a curve, but the integral is not the area. The integral lives in its own realm. It literally lives in its own realm. The integral is a sum. Yes, it is. If you look at the symbol of the integral is an S. S for sum. Exactly. One of the many applications of the integral is finding areas and volumes. You always thought it looked like an F. Well, yeah, kind of. You're sort of missing the little stick behind, aren't you? The integral has almost limitless application. I mean, it's literally unfathomable how much you can actually do with integrals. There is also there is a theory of generalized integrals, which I have started to work with recently, but the complexity gets up so fast. It's really difficult to follow. So it's better to have some little basics very clear and very solid, and then who knows, maybe when more complicated things arrive, you will be ready. Also consider that I haven't said if, I have said when. I mean, in the end, what gives sense and direction to life is constantly challenging your own limits. And that's a very broad statement. Like, please don't take it too strictly. So okay, now, so we have a huge empty whiteboard and a couple of minutes left. So I'm going to go back in before. Now it's the time where I ask the questions. How was the exam? I know someone has said it was easy, but all the rest of you are kind of a little tired. Maybe you don't want to spoil the fun where you open Laddock and find you got max grades. So yeah, tell me, was it difficult? Do you think it could have been shorter, longer? Maybe there was one exercise you had problems with. If that was the case, on the workshop on Friday, I plan on solving the exam with you guys. So please don't miss that one. Was this thing we always did back in the times where I was studying single order calculus and ODEs and all that, which the professor would take a full lecture only to solve the exam in the whiteboard. It was good and terrible at the same time. The limit of the cosine of e in power x as x approaches 2. Come by the workshop on Friday. I will solve the exam. And you will see it's a little bit soon to start spoiling stuff. So yeah, live with the emotion, live with the intrigue. Also, you can attempt to resolve the exam at home. You may notice that the environment changes greatly the outcome. All right. So it's a little bit early, but I think we can call this a day. The topic of Riemann sums really doesn't stretch that much. So this is what we can do. Please work on the exercises so you can get a good understanding of what Riemann sums are and why they are used to build the integrals. I'm going to go to my office and see if I got a pile of exams this large to correct, so we can give you your grades as soon as possible. And I will see you on Thursday, I guess. Thank you guys for joining, and have a great day.